So during the last lecture last week, we got to find the domain of a radical function containing two variables. And well, so of course we use the same guidelines. Whenever you have a radical function of an even index, that is like a square root, like a fourth root, sixth root, etc., would you set the argument, I mean not the argument, the radicand greater than or equal to 0. So it's the same guidelines, you know. It's just now we think of these functions with two variables at a time. All right, so well, in this case, again, a function f of x, y will describe a surface in space. So then these two variable inequalities or equations we end up with are going to describe in a way the traces or the projection onto the xy plane. So we did an example. Let's have a look at another example, one involving an arc sine function, an inverse sine function. Well, so find the domain and, well, not the range, just the domain of the function f of x equals to arc sine of y minus x. So in this case we have two variables at the same time, not just one. Okay, so again give a complete description of the domain, including a sketch in the xy plane in a similar way we did it for the previous example. All right, so where do we start? Well, in a similar way we we look at the radicand in the previous example. We set it greater than or equal to 0. So for the arc sine function, well, again, we are going to bound the argument, that is this guy, y minus x, between -1 and 1. All right? So, okay, that means we're going to set y minus x less than or equal to +1 and greater than or equal -1. And let's solve the inequality. Well, what is this going to give us? Well, so now that we have gone from 3D to 2D, well, typically, well, because in this case, this is not a conic section like the previous example. In this case, we have a compound inequality, and we need to, in a way, establish what it is, the dependent variable and the independent variable. And keep in mind that when we have x and y's, the dependent variable is y, the independent variable is x. All right, so that means let's isolate, not isolate, but rather isolate the y in the center or in the middle of the compound inequality. We do that by adding x to three sides of the inequality. That's going to leave us with x minus 1 less than or equal to y less than or equal to x plus 1. All right, what does that mean in terms of the way we're going to solve the inequality? Well, so, okay. Let's recall our theory of inequality, of compound inequalities. That means that whenever you have the three-sided inequality, this means the same as solving x minus 1 less than or equal to y and y less than or equal to x plus 1. I'm a little worried about the first inequality because typically we read inequalities containing two variables with the dependent variable on the left-hand side of the inequality. For the second case, it's fine. We have the y on the left and x is on the right-hand side. I'm going to reverse the order of the inequality. I'm going to write it like y x minus 1. But again, keep in mind that every time you reverse the order of an inequality, we also need to reverse the inequality symbol. That is, it becomes greater than or equal this time. You know, like 4 is less than 5. If you reverse 5 compared to 1 to 5 compared to 4, then you would need to switch or reverse the inequality symbol to greater than or equal, right? Or greater than, depending on the case. All right, so that means these two inequalities, we need to graph them together, right? Okay, so let me do a couple of Cartesian planes. And so that's going to be, wait, it didn't give me, yeah, what I wanted. So that'll be So the first inequality, I'm going to treat it like an equation for a second. So that's going to be y equals x minus 1. So that's just a diagonal line, y equals to x minus 1, where the y-intercept is at negative 1. All right? So I'm just going to draw this line right here. While the second inequality, for the second inequality, I will plot y equals x plus 1. That is the same diagonal line, but actually this time with a y-intercept at positive 1. All right, let me do something like this. All right. So, but in this case, well, we're not just graphing the equations, we're graphing inequalities again. Y greater than or equal x minus 1. Well, you have a couple of options to graph these inequalities, interpreting the inequality symbol, which is not necessarily a shortcut, but I find it quicker and more practical. Or you can simply substitute your favorite test point. Typically is the origin, but I'm gonna use the inequality symbol. So this diagonal line again will divide the Cartesian plane into an upper and a lower region. Greater than or equal means above, so I'm gonna shade above. So it is. We'll add this way. So that means all this above the line, right? Okay, and for the second inequality, y less than or equal x plus 1. So that'll be below, that means below the second line, like this. Okay, so now I need to put together these two sets. So in a similar way we did with the vector valued functions intersecting the number lines, well, in this case we are intersecting the what's it called, the regions, not intervals, because again in this case we're looking at regions, no longer at intervals. So let me do another what's it called, another Cartesian plane to show the overlaps of these two sets. That is, on the one hand, so that's going to be this line and this other line. Whoops. Oh, come on. There we go. Okay. So I don't know what happened here. Okay, there you go. Like this. And so again, graphing these two sets together, that means below the upper line and above, wait, what? That's not, oh, I see why. Okay. So that is below the upper line, the upper diagonal line, and above the lower diagonal line. So what are we going to do here? Well, we're going to look at the overlap of the two sets. That is where the pink and the blue kind of combine to create this purple shade, right? So that is going to be our domain. So let me do a quicker like this. So essentially we're just looking at this part, at this region, the purple one, right? Oops, let me. So the overlaps in this case. Well, how about we see this graphically? I mean, this is still graphical, but I mean in 3D. So for the function arcsine of y minus x. So I'm going to go to GeoGebra, and I'm going to plot the function. What is that? That is z equals to, okay, z equals to arc sine of y minus x. Okay, and we're gonna get this weird graph. Well, Okay, so this is the x and the y axis. Okay, that's the usual perspective, x, y, z, the usual perspective we look at. But in this case, I don't know how to stop this. Oh, there you go. So let's look at this region from the top. Does that look like that intersection between the two sets? Well, in this case, this looks weird, I guess, because of graphing issues. I don't know. So, well, actually, yeah, it looks very pixelated. Maybe I was thinking it was on a graphics card issue or something, but I don't think it is. Well, actually, look at the sideways function. Doesn't that look like the arcsine function from the side? All right. But from the top, it's the intersection between those two lines, of those two regions, in this case, those diagonal lines. All right, so that's how it looks like in space. Let me see if I can zoom it out a little better. Maybe that fixes the issue. No, it doesn't. So, and that's how it looks like in space, all right? So that's what we get the projection onto the xy plane, which is what we did by hand. All right. Let's go back to the notes, and well, now let's talk about functions of four variables, one dependent and three independent variables. Well, for this one, rest assured you're not going to be asked to graph, because think about a function of four variables, right? So how are you going to input three variables and get a fourth variable as the output? That's like thinking in four dimensions, right? So I mean, we're barely grasping the third dimension now. We now think of a fourth dimension. Well, that's weird. So in this case, all we're going to do is use the guidelines to find domain, the same ones we've been working on. For instance, okay, find the domain of the function g. Oh, hold on. I need to go back to the previous exercise and write our result in set builder notation. Hold on, we're not yet. So actually, there's like three ways to represent this, and I'm going to show you the three of them. At least the three I can think of. So, for instance, number one, the domain, all the order pairs x, y, such that number one, you can just copy and paste the initial inequality, that is -1 less than or equal y minus x less than or equal to 1, right? That is our domain as a set builder notation. Well, is there another one? Well, there's two more at least. Number two, the one for which we solve for y, that means we leave it in the center of the compound inequality. All the order pairs x, y such that essentially y is greater than or equal x minus 1 and less than or equal x plus 1. And the third one, there's a third one. So if you know your inequalities, your compound inequalities versus absolute value inequalities, so you might remember this from intermediate algebra, that the first version, y minus x being greater than or equal -1 and less than or equal to 1, it's the same as saying x y such that absolute value of y minus x less than or equal to 1. All right, so those are the three ways to express this solution set. Yes.
Like in an exam, would we have to like write all three? Or do we
No, your favorite one.
Okay.
The one you feel more comfortable with. The last one is more compact, and that also means you can see the difference between, or tell the difference between absolute values and all that, right? So, but any of them is fine. Right? Any of them is fine. All right, now let's talk about three variable functions. So three independent ones. So we have g of x, y, and z equals the quotient between a logarithmic function and polynomial. Yes, just z, it's technically a polynomial. So number one, red flags. Number one, we cannot have z equals to 0 because the function is undefined. And also we have a logarithmic function with a restricted domain. So we're going to use all those guidelines. Number one, for the logarithmic function, we're going to set the argument x plus 2y greater than 0, not greater than or equal. That's for radicals of even index, not greater than, just greater than rather. And well, let's solve the baby inequality for y. That is 2y greater than negative x, and y is greater than negative 1/2 x. All right. So that's one of the red flags for this function, or for the conditions for this function. All right. What about the denominator? Simply, z cannot be 0. Otherwise, again, we just discussed that part. So let's write the domain. So we have everything we need to write the domain. And by the way, there's no interval notation for functions of multiple variables, just set builder notation. Now, here, when we talk about functions of two independent variables, we use the order pair x, y. Here, for functions of three variables, we're going to look at all the order triples such that, number one, just copy this inequality, y greater than negative 1/2 x, comma, z cannot be equal to 0. All right? That means all the numbers, okay, greater than means above the diagonal line, which by the way would be dashed, right? It would be dashed because of the greater than only. So, and well, as long as z is not equal to 0 as well. All right, so that was another example. Let's do one more and then look at graphs. Find the domain of the function f of x, y, z equals the square root of negative x plus the cube root of y plus the square root of z. All right. Number one, the term in the middle with the cube root, that is a radical function of an odd index. Well, those have no restrictions at all, so we're good. However, the first and the third term are radicals with an even index, so they're going to have restrictions. So number one, let me write down those restrictions. So that means for the first term, negative x greater than or equal to 0. And then for the second term, since it's an odd index, y is simply all real numbers. And lastly, for z is greater than or equal to 0. Well, actually, we need to solve the inequality for negative x greater than or equal to 0. I know it's just 0, but still you want to isolate the x by dividing both sides by negative 1. All right, x greater than or equal 0. Do you guys agree with this result? Yes? No? What about it? Exactly. Every time you multiply or divide an inequality by a negative, you need to reverse the inequality symbol, right? So let's reverse it. Okay, so y it's all real numbers, no problem. Z is greater than 0, greater than or equal to 0, no problem. There's nothing else to solve. We're just ready to write the domain of this function, x, y, z. That is, all the numbers x that are less than or equal to 0, y is all real numbers, and z is greater than or equal to 0. So that is our domain. And guys, it's very important that we get used to this notation, to this set builder notation, because we're going to use it pretty much for the rest of the semester, at least when we get from chapter 16 and on, because we're going to use this to describe the regions of integration that are going to give us the shape of a solid, for which we're going to evaluate a triple integral, a double integral to find area, volume, mass, or in the last chapter to find surface area, upper surface area, the flux across the surface, what else, Stokes' and divergence theorem at the end of the semester. And well, this is like indicating where and how do we and how are we going to look at this solid. All right, let's sketch graph up to variable function. So, okay. So the first one, f of x, y equals to x plus 3y plus 6. Well, so all we need to do is replace our f of x, y with a z. So z equals to x plus 3y plus 6. And well, if we look at this equation, we have worked with the a bunch of times already. All right. So what's that equation of? What does that represent? What surface represents? You just had an exam on this, actually. What is that? A plane, right? A plane. So that means negative x plus, or rather minus 3y plus z equals to 6. And there's a couple of ways, there's a bunch of ways to graph this plane, but the easiest one is by finding the intercepts, you know. Remember the peekaboo, two variables at the same time? But well, I don't want to, well, actually I'm going to do it real quick. So in this case, however, I'm going to get negative intercepts. So that's what I don't like about this exercise. I should have changed the signs or something. But anyway, so the x-intercept make the y and the z equals to 0. The x-intercept is at negative 6 over here, somewhere there. And the y-intercept, by making x and z equals to 0, that's going to give us negative 3y equals to 6, so that's negative 2. And lastly, x and y equal to 0 to obtain the z-intercept. That's going to take us to z equals to, so equal to 6. So I'm going to graph the plane, and I'm going to try to make it look like it's on the back of the z-axis. On the what would that be? 1 to the third octant, right? The equivalent of the third quadrant in space, if you will. All right. It's gonna look like a pyramid, if you will, or like a tetrahedron, however you want to call it. All right. Okay. Letter B. For letter B, let's graph f of x equals to the square root of 4 plus x squared plus y squared. Okay, so number one, we need to define a function to replace our variable, our symbol f of x, y with the variable z. All right, that is the square root of 4 plus x squared plus y squared. And well, by itself, it doesn't tell us that much, you know. So, what is this? Okay, let me square both sides to get rid of the radical. That's going to give us z squared equals to 4 plus x squared plus y squared. All right. So that's going to give us one of the quadric surfaces. Well, which again, you guys are not expected to memorize this or to know these functions, of course. So, and I'm just gonna give it away. This is a cone. Actually, this is a, well, elliptical cone in general, but because of the coefficients of x and y being the same, well, that makes it a circular shape, right? So, but I mean, how are we going to graph this this cone right here? Okay, so this is what we're going to do. We're going to give z some values. Give z some values. So that means I'm going to choose z equals to 2. Convenient value that, well, I already know how this works. I've done it a few times. So for z equals to 2, I'm going to replace 2 squared equals to 4 plus x squared plus y squared. So that is 4 equals to 4 x squared, plus 4x squared plus y squared. That's going to give us x squared plus y squared equals to 0. All right. So, well, we'll talk about it in a second. Let me get just some of the equations, some of the traces, if you will, and then we're going to put this all together to get the graph. All right. So let me choose another value here. Z equals to 4, for instance. So for z equals to 4, we're going to get the following. That is 4 squared equals to 4 plus x squared plus y squared. That is 16 equals to 4 plus x squared plus y squared. So let's subtract both sides of the 4 to get a 12. On the right hand side, that's x squared plus y squared equals to 12. All right. Let's do one more trace. The trace where z equals to, what's that? Z equals to, I have 5. All right. I mean, in the end, you can choose your favorite values, except some there could be some restrictions. We can talk about that later. All right. So for z equals to 5, that's 5 squared equals to 4 plus x squared plus y squared, and that's going to give us 25 on the left hand side. So 25 equals to 4 plus x squared plus y squared. That's going to give us x squared plus y squared equals to 21. All right, let's talk about these traces here. Let me highlight them. This one, that one, and that one. Okay, so the first equation, x squared plus y squared, what's that? Is that an actual curve? If so, what kind of curve is that?
Parabola.
It's a parabola, so we have both variables squared, all right? It looks like a circle, but hey, do you look at the, hey, what happened here? Look at the what's it called? Okay, look at the right hand side of the equation. Look at the radius of that circle. I mean, is there a circle of radius 0? What is that anyway? What is that anyway? What is that then? It's just a point, right? Just a point 0, 0, where the 0, 0, where the z value equals to 2. All right. What about the remaining two equations? X squared plus y squared equals 12. X squared plus y squared equals to 21. Those look like what? Circles this time, right? I know the radii might look weird. They're not perfect square, but they're still circles. Well, how are we going to graph this? So I'm going to go 1, 2, 3. And I'm going to go, okay, I'm going to plot the point 0, 0, 2. That's easy to plot. 1, 2. And then from there, when z equals to 4, 1, 2, 3, 4, I'm going to have this circle of radius square root of 12. So with some perspective, I mean, because again, it's kind of hard to plot, but I'll show you how this looks like in the end. And when z equals to 5, that's going to have another circle. And this is going to give us the cone we were describing. All right. So that's another way to graph surfaces using the traces for different values of z. But it may get hard when the minute we get with functions that are not like the common, what's it called, the common quadratic surface. Like typically this is easy for cones, paraboloids, what else? Maybe ellipsoids, maybe spheres, at least in the first octant. Well, actually, what we're doing here about getting the traces to plot a surface in space, it's in a way a prep to what's coming up: contour maps and level curves. Okay, I'm pretty sure you have seen this before, like where in the news, in video games. I'll show you how this looks like. Well, number one, let's define this. So a contour map, it's a surface that is created by projecting the different traces when intersecting a surface with a plane in the z direction. So when we intersect, for instance, this cone right here, and we intersect it with a plane horizontally, if you will, that works like a knife, if you will. Okay, so this intersection will be, well, in this case, between a plane and a cone, it's going to be circular. And what are we going to do? Slam it onto the xy plane to see its projection, its shadow, if you will, right? Like having the sun at the top and intersecting this plane at different at different heights. So that's going to give us different shadows. Well, where have you seen this before? So let me look at this map right here. All right. So this map right here, it's called a map for isothermals. Well, and again, I'm pretty sure you've seen these maps, especially these days where we're getting to get high temperatures due to the weather change, right? So, and typically you have a color nomenclature on one of the columns or one of the rows at the top or at the bottom to indicate, those colors indicate temperatures, and typically red is related to a hot temperature, blue and white is related to a cold temperature. So that's how it goes on the scale. But the question is, what are these lines that divide the colors, that divide the regions by colors? For instance, these are called isothermals. Isos, which comes from Greek, isos is the same, thermals, temperature. So that means if you walk along those lines, you're going to be at the same temperature all the time. That means, for instance, if you want to walk from, okay, Chicago is somewhere here. Okay, from Chicago, and I follow this contour right here, I can get to, I don't know, is that the limit between California and Oregon, right? So it's not, no, Portland, it's somewhere here, I think. Anyway, so that means if you walk along that trajectory, you will be at the same temperature because, again, isothermal, I mean, walking or driving or flying, whatever you're doing, of course, due to the time, these temperatures are subject to change, you know, with the minute or with the hour, whatever. Another example, in video games, for instance, okay, let me show you the map for The Legend of Zelda Tears of the Kingdom. How many of you play Zelda? So, a few of you. So, maybe you've noticed something interesting about the map, about these curves right here. Well, those curves, which are also called the level curves, that is where as Link, the character in the video game, is walking and it's exactly at the same height every single time. So a different profile to see these curves, see how it actually gives us an idea that there is a hill, a mountain, or a depth or something, right? So for instance, to have a better overview of these level curves, have a look at this profile picture here. So for instance, if you have a mountain here, so these are the different trajectories at which you will be at the same height. Well, 1100, well, what are these? Meters, for instance, 1200, 1400. And if you were to project this onto the XY plane, you would get this like circles or closed curves, so to speak, right? That create regions which are the same as the map I just showed you for the map for the Legend of Zelda video game, all right? So, and well, in this section, we're going to learn how to graph this kind of level curves. But of course, we're not going to do anything to elaborate like that. We're going to go simple. We're going to go with the known and common surfaces. All right. Okay. So given the function f of x y equals to 6 minus 2x minus 3y. Sketch the level curves for k equals to 0, k equals to 4, and k equals to 8. Describe these level curves and also identify the type of surface represented. All right? Okay, again, number one. Z equals to 6 minus 2x minus 3y, all variables raised to the first power, a plane, all right? Now, what is a plane going to project? Well, number one, so this is what we're going to do. So we are going to set z equals to some k in this case. That z is going to be the equation of a plane that will cut the surface, you know. So when that plane cuts the surface, There will be an intersection line, maybe an intersection curve, an intersection circle, an intersection ellipse. Well, depending on the nature of the surface this plane is intersecting with, right? So, well, in this case, to get this done, we're going to give some values of k in a similar way we did before. So essentially, we're getting the different traces for different heights. So for k equals to 0, so for k equals to 0, we're going to get the following. 0 equals to 6 minus 2x minus 3y. That'll give us 2x, 3y equals to negative 2x plus 6, and divide both sides by 3. That's going to give us negative 2/3 x plus 2. All right, so that is the first trace. All right, and well, what does that equation represent? Notice in this case it's only a two variable, one independent, one dependent. What does that describe? What is that? A line. It's just a line. All right. So we will get a better picture of this later using GeoGebra. I'll show you in a second. Okay, number 2, for k equals to 4. Let's see. For k equals to 4. So that is, replace the z with a 4. That equals 6 minus 2x. And what's that? Minus 3y. So let's subtract 4 on both sides and add the 3y to both sides. Okay. Let's do that simultaneously to get the y solved by itself again. So let me make this look like a 4. There you go. So that'll be 3y equals to 2 minus 2x. And that's going to give us y equals 2/3 minus 2/3 x, which is going to be another line. All right? That's going to be another line. All right. Let's do one more trace, one for k equals to 8. So for k equals to 8, we're going to do the same essentially. So 8 equals to 6 minus 2x minus 3y. Okay, let me subtract the 8 on both sides and add the 3y again. That's going to give us, that's, okay, let me turn this into a different color. That'll be, 3y, whoops. 3y equals to 6 minus 8, that's negative 2. Minus 2x, and that's going to be y equals to negative 2/3 minus 2/3 x. And again, this is going to be another diagonal line. So notice how these three diagonal lines have in common the same slope. You know, all they differ by it's the y-intercept. Okay, let me plot this line as best as possible because look at the intercepts. Look at the intercept. They're a little. They're fractions. It's going to be a little bit hard to plot them. So I'm just going to give a rough sketch. So number 1. Negative 2/3 x plus 2. I'm going to go to the y-intercept at 2, and then I'm going to dive 2 units and run 3 units. Like this, all right? And then for the second trace, I'm going to go 2/3. So that's roughly here. And also I'm going to go down 2 units and forward 3 units. Like this. All right? And the other trace, the last one, that I'm going to go down to negative 2/3. That's roughly here. And I'm going to do another trace similar with that intercept. That's too low. Right? Something like this. Right? It's a bit hard to plot this by hand. Actually, I have a GeoGebra file for this. Okay, so let me go about that. Okay. It's gonna take a second. There you go. No. don't want this. Local file, level curves. All right. So we have this this applet in GeoGebra for which we can actually change the function, so we can see the different level curves and the contours as well. So I'm going to change this function to 6 minus, what's that? 2x minus 3y. Click enter. Well, actually, let me zoom in, zoom out to get rid of that circle. Well, what's going to happen here? So here we have a plane. Here we have a plane in space. So in the the typical x, y, z perspective, we get to see this plane. Okay, let me see if I can lower the lights so you can see it better. So here, these different values of C are the different values of K that we did in the previous exercise. So for instance, all we're going to do, so let me put it on the side from a different perspective, so you can see for different values of C, how we create the different lines, right? Those different level curves. Well, in this case, they are level lines, but they're still considered curves. Now, this H plane, that's the plane that intersects with the surface to project those lines. So, do you see how the plane projects with the other plane, intersecting at this line that is in dark color, in black actually? So the shadow of this line right here, it's in red right there. It's maybe this one right here. All right. So think of a geometric shape having a diagonal plane as a side. For instance, you can think of a pyramid having different sides as different planes. So if you're walking around a pyramid at the same height at different levels, the shadow, the projection will be these diagonal lines. The next example will be a better example because it's going to give us a more interesting shape, by the way. So let me go back to the notes. Now let's, given the function f of xy equals to x squared plus y squared, sketch the level curves for c equals 0, c equals to 4, and c equals to 9. All right, so, well, z equals to x squared plus y squared. Any idea by just looking at the equation, what kind of surface would this be? Circle. Okay, let me give you a hint. The dependent variable is raised to the first power. Get rid of one variable at a time of the independent variables. That's going to give you an idea of what it is. Paraboloid, right? If I get rid of, say, y squared, that's z equals to x squared. That's going to be the xz trace, which is a parabola. And likewise, this is going to be, if I do that, that's going to be a parabola in the yz plane. So that's going to create the armor of a solid in the shape of a paraboloid. Okay, so all right, let's generate this level curve. So for the different values of c this time, so this guy is going to be called c this time. So c equals to 0. That's 0 equals to x squared plus y squared. For c equals to 4, that's 4 equals to x squared plus y squared. And lastly, for c equals to 9, that's 9 equals to x squared plus y squared. And we have already looked at equations like this. You know, again, that x squared plus y squared equals to 0. Yes, it looks like a circle, but I mean, there's no such thing as a circle of radius equal to 0. So that's just, again, a point, you know, a point where the input x, y are both zeros, and the output c, which is the z variable, is 0. So that's just going to be the origin in space. All right. For c equals to 4, x squared plus y squared equals to 4. That's a circle of radius 2. Agree? What about x squared plus y squared equals to 9? That's a circle of radius 3. So we're going to generate different level curves that are going to look like circles. So, okay, let's do this by hand, and then I'm going to show you how to do this using GeoGebra. So, that's the origin, and then I'm going to go to c equals to 4, 1, 2, 3, 4, and I'm going to draw a circle of radius 2. Roughly, I mean, with perspective, it's hard to get the actual radius of whatever the circle. And all the way up to 9, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to draw another circle of a radius 3. And that's going to give us the paraboloid. Notice in this case, it's not a cone. You see the traces, they actually look like a parabola. And I'm going to make the vertex look a little more curvy, not a sharp corner like the cone looks like, you know. That's very common in the cones. All right. So this is how we plot, surfaces using these level curves. Now let's generate these level curves using the GeoGebra app I just showed you. So I'm going to go to the applet, to GeoGebra. Let me zoom in, zoom out, change the equation. So that's going to be x squared plus y squared. All right. So now we have our paraboloid, and let me start at c equals to 0. Let me initiate this. So this is what's going to happen. I'm going to increase values of c. So for instance, for c equals to 0, we just have the origin, this point, which is the intersection of the three axes. I'm going to increase the value of c. That's going to give me the intersection between the plane and the paraboloid, whose intersection looks like a circle, but actually the level curves are those intersections slammed onto the xy plane. That is their shadows, which you can see in this Cartesian plane, but you can also see these projections in the space right here. If I rotate this, you can see them better. If I change the perspective from top to bottom, you can see this as dashed lines. So I'm going to keep increasing the values of c. That's going to give me more and more of these level curves. You see how they are all concentric circles, and again, those are projected onto the xy plane. All right. So that's about level curves. Like I mentioned before, well, this is not we're not going to get too crazy about them, but still, let me show you another one that it's actually animated. I believe it's level curves number 2. Okay. Yes, okay, so we have this weird surface here. Notice how this plane is going up and then it's going down. And do you see those curves in blue being generated as it goes up and down? Well, of course, think about these curves in the plane. Well, these are very complicated curves to do them by hand. So just look at the generating function, x squared plus 3xy minus y to the 4. Well, that's not one of the known surfaces we know, like the 6 basic we learned back in the previous chapter. So for this one, I'm just showing you an animation so you can see how these level curves are generated or created by intersecting a surface with a plane and the intersection curve, which gets projected onto the xy plane. So for instance, for a quiz or an exam, I'm going to give you something simple like a cone, like a paraboloid, a hyperboloid of 2 sheets maybe, which will project hyperbolas. Well, something that it's easy to plot, that it's easy to describe both algebraically and graphically. Nothing as fancy like this, all right? Okay, let's go back to the notes. Level surfaces. Level surfaces, it's like the analogous of level curves. You know, but in this case, we would be describing 4-dimensional functions where we have 3 variables as the input and 1 variable as the output. How are we going to visualize such a 4-dimension? No, well, that 4-dimension will be a constant, and well, that 4-dimension being a constant will take us to 3 dimensions, to different shells, if you will, of a surface. Okay, for instance, describe the level surfaces, not curved surfaces, for f of x, y, z equals to x squared plus y squared equals to z squared. Okay, so that means we're going to call this guy k or z. It doesn't matter. All right, it doesn't matter. So and let me give some values here. K equals to 1. That means 1 equals to x squared plus y squared equals to, plus z squared. And then k equals to, how about 4? That equals 4 equals to x squared plus y squared plus z squared. And for k equals to 3, no, not 3, 9. 9 equals to x squared plus y squared plus z squared. Okay, let's describe those 3 surfaces. What do they look like?
Spheres?
Spheres, right? So spheres. Okay, what about the first one? Radius 1, also known as the unit sphere. What about the second one? The sphere. Radius 2. What about the third sphere? Radius 3. Well, it's hard to plot these level surfaces because the graphs overlap. But I'm going to try my best to show this. So, for instance, for the unit sphere, I'm going to think of. Let me use green. Okay, so that's 1, and that's 1. So I'm just going to do the part of the sphere in the first octant. So that is the first sphere, all right? Okay, then I'm going to put on top of that another sphere of radius 2. I'm going to use a different color. So that's the second one. Alright, so we have another sphere, a different layer, what else? Let me use a different color. That's a sphere of radius 3. But in the first place, they don't look like spheres because I'm just doing the first octant. But with some imagination, we can think of these surfaces extended on the octants on the back and below to give rise to spheres. And we'll see how the colors kind of overlap, so it's hard to see what it really is. So with some imagination, think of an onion, for instance, right? Onion, assuming it's perfectly spherical. Well, each layer in the onion, it's going to be one of these shells right here, or those candies that have different layers of colors. I think they're called what's that? Dough breakers, I think there is. Yep. And rocaletas with the ones with chili and different flavors as well. So those are like, you can think of those like like level surfaces, not level curves, level surfaces. For the recording. So. The body mass index, called BMI, for an adult human is given by a function of 2 variables that depends on W and H. That is W over H squared, where W is the weight measured in kilograms and H is the height measured in meters. So let's talk about domain restrictions for this function. But first of all, let's list the independent variables. So what are the independent variables here? W and H, right? So W and H. And the dependent variable? That's B, all right? Now, what is the domain of the function? I mean, yes, in the numerator for w, you have a polynomial, right? Apparently, no restrictions to it, right? Because it's a polynomial. However, in our context, it may have some restrictions. So, domain, all the order pairs, first of all, not x, y, but w, h, such that, what about w? Can w be a real number? I mean, algebraically, it can be a real number because that w is not inside of a radical or as the as the argument of a logarithm or the argument of an inverse trig function. So no restrictions. But in this case, the context of the situation is going to give us restrictions. So what would be the actual domain of w?
Greater than 0.
Greater than 0, right? So can a person weigh negative kilograms?
No.
Is there a person with 0 kilograms? Well, that's no person, right? So w greater than 0. What about h? Oh, h squared in the denominator would be undefined if h equals to 0. But is 0 the only restriction here? Also negatives, right? So there's no negative heights. And there's no 0 height. Well, for two reasons. Algebraically makes the denominator 0, and physically a person with 0 height, it's no person, right? So h has to be also 0. They're asking us to evaluate B of 51. That is the body mass index for a person whose weight is 50 kilograms and his height is 1.5 meters. That is B of 50, 1.5. That equals W, that's 50 over 1.5 squared. Using a calculator, that's going to give us 22.2. That's our body mass index. All right, how can a person lower their BMI? How is that possible? Well, algebraically, there's two ways, but physically, there's only one way. What is that? Lose weight, or yeah, lower W, right? Lowering W. Another way is to increase the value of h, but I mean, can you get higher and higher and higher? I mean, yeah, that's why child are recommended to play basketball, right? To get taller and taller, right? But well, there is a limit, right? So there's no, you cannot get as high as you want, right? So that's the only solution here. And with this,